There is a planet in our sky almost the same size as Earth. Its diameter is only about 5% smaller. Its gravity feels nearly identical. It formed from the same cloud of rock and metal in the same early solar system at nearly the same time. On paper, Venus and Earth should have grown up alike. Some climate simulations suggest that early Venus may have once been far milder than it is today. It may even have held shallow oceans for millions of years. Not proven, but possible. And yet today, the surface of Venus reaches about 465 degrees Celsius, hot enough to melt lead. The air presses down with more than 90 times the pressure we feel at sea level. No spacecraft has survived longer than a few hours there. Its atmosphere is almost entirely carbon dioxide. Thick clouds of sulfuric acid hide the surface from view. It rotates slowly and backward. A single day on Venus lasts longer than its year. Earth and Venus are neighbors. At their closest, they come within tens of millions of kilometers of each other. Two worlds built from the same materials, one covered in oceans, one sealed beneath crushing heat. If they began so similarly, how did their paths separate so completely? What small difference tipped one world toward stability and the other toward permanent runaway heat? Was Venus unlucky, or did it cross a boundary that Earth still lives dangerously close to? Tonight, we look at the thin line between habitable and hostile and how a planet almost identical to ours passed it. But before we begin, I'd love to know where in the world you're listening from tonight and what time it is there. Your comments are one of my favorite parts of this little community. If these gentle journeys help you unwind, a like or subscribe truly helps this corner of science keep growing. Now take a slow breath, let your shoulders loosen, and together let's drift toward the moment Earth's twin became something unrecognizable. Long before planets had names, before oceans or atmospheres, or the slow turning of seasons, there was only a cold, drifting cloud suspended within a quiet arm of the Milky Way. This molecular cloud, composed of hydrogen, helium, and faint traces of heavier elements forged in older stars, moved almost imperceptibly through space. A nearby stellar disturbance, perhaps a supernova shockwave, passed through it and disturbed its balance. Gravity began to gather what had once been diffuse. Regions thickened, density increased, motion accelerated inward. What had been a scattered mist slowly drew itself into a single tightening spiral. At the center of that spiral, pressure and temperature rose steadily. Atoms collided with growing urgency. When the core became hot enough, nuclear fusion ignited, hydrogen fused into helium, and light emerged for the first time from the newborn sun. The remaining material did not vanish. It flattened into a rotating protoplanetary disk, a vast, luminous ring of gas and dust circling the infant star. Within this disk, particles drifted and collided, first clinging through static forces, then binding through gravity. Grains became pebbles. Pebbles became kilometer-wide planetesimals. These bodies moved in crowded orbits, colliding, merging, breaking apart, and forming again in an endless choreography of impact and accumulation. Closer to the sun, temperatures were too high for volatile compounds to remain solid. Water, methane, and ammonia evaporated easily. What endured were metals and silicate minerals, resilient materials capable of withstanding intense heat. From this inner region, the rocky planets began to assemble. Venus and Earth emerged from neighboring zones of the same disk, drawing from nearly identical reservoirs of iron, nickel, silicon, magnesium, and oxygen. Their bulk compositions reflected the chemistry of this shared birthplace. Molten surfaces churned as radioactive decay and frequent impacts generated immense internal heat. Each young world differentiated, heavier metals sinking toward forming cores, lighter silicates rising toward primitive crusts. In those early tens of millions of years, the inner solar system remained unsettled. Orbits shifted subtly under gravitational influence. Leftover debris from planetary formation continued to wander through space. Asteroids and protoplanets crossed paths with growing worlds, striking with energies that reshaped entire hemispheres. This era of heavy bombardment left scars that would later be preserved on airless bodies like the Moon and Mercury. On Earth and Venus, repeated impacts melted crusts, vaporized surface materials, and may have temporarily thickened early atmospheres with released gases. Water, essential to later histories, did not necessarily originate solely from within these planets. Beyond the frost line, farther from the sun, icy bodies formed where temperatures allowed water to remain solid. Gravitational interactions with the giant planets scattered some of these icy asteroids and comets inward. When they collided with the rocky worlds, they delivered additional volatiles, including water molecules locked in minerals and ice. Over time, as impacts decreased and surfaces cooled enough to allow condensation, steam in the atmosphere could settle into liquid form. Both Earth and Venus likely experienced intervals when water accumulated at their surfaces, at least briefly, under conditions that were still stabilizing. Thus, from the same collapsing cloud, shaped by the same disk of gas and dust, and assembled through the same relentless collisions, two neighboring planets took form. Their cores solidified beneath molten mantles, their crusts thickened, their atmospheres gathered from volcanic outgassing and extraterrestrial delivery. In composition and origin, they were siblings born of identical processes, set in motion within the same luminous nursery of a young star. Clues about Venus's earliest chapter do not rest on visible shorelines or preserved sediments, but in subtle ratios carried high above its surface. Within its atmosphere, atoms of hydrogen appear in two forms: the lighter common variety and the heavier isotope known as deuterium. Spacecraft measurements have revealed that deuterium is far more abundant relative to ordinary hydrogen than it is on Earth. This imbalance suggests that vast quantities of lighter hydrogen once escaped into space, leaving the heavier isotope behind. Such enrichment is often interpreted as the fingerprint of ancient water, because when water vapor rises and breaks apart under ultraviolet light, hydrogen is the first to drift away. The numbers do not offer a picture of oceans, yet they whisper of reservoirs that no longer remain. Computer simulations extend this quiet suggestion into climate. When planetary scientists adjust early atmospheric compositions and solar output within their models, some outcomes allow Venus to maintain surface temperatures cool enough for liquid water, at least for extended intervals. These scenarios depend on clouds reflecting sunlight efficiently and on atmospheric circulation redistributing heat across the globe. In certain configurations, a slow rotation rate may even encourage thick cloud formation on the day side, increasing reflectivity and moderating warming. Under such conditions, the planet need not have been temperate in a terrestrial sense, but it could have avoided the extreme state it inhabits now. This possibility unfolds against the backdrop of the faint young sun paradox. Billions of years ago, the sun radiated less energy than it does today, perhaps 20 to 30% dimmer. For Earth, this reduced brightness poses a puzzle, since geological evidence indicates the presence of liquid water early in its history, despite weaker solar heating. Greenhouse gases are thought to have compensated, trapping enough warmth to prevent global freezing. Venus orbiting closer at about 0.72 AU would still have received more solar energy than Earth, yet that additional input may not have been overwhelming under a fainter sun. The balance between incoming radiation and atmospheric cooling could have been delicately poised. Distance from the sun shapes planetary climate in a steady mathematical way. Energy decreases with the square of orbital radius, so even a modest shift inward increases solar flux significantly. For Venus, that proximity meant nearly twice the sunlight Earth receives today. Early in the solar system's history, however, the reduced luminosity softened this difference. If Venus possessed sufficient cloud cover and a moderately thick atmosphere rich in water vapor and carbon dioxide, it might have sustained surface temperatures within a range compatible with shallow bodies of liquid water. These would not necessarily have resembled Earth's deep oceans, but perhaps broad, warm seas or scattered basins filling lowlands across volcanic terrain. Over millions of years, such waters could have interacted with rocks, altering minerals and influencing atmospheric chemistry. Liquid water dissolves carbon dioxide, participates in weathering reactions, and transports heat efficiently. Even limited oceans would have introduced feedback processes that moderated extremes. Yet this stability would have been conditional, resting on a narrow equilibrium between solar input, atmospheric composition, and planetary albedo. As the sun gradually brightened and volcanic outgassing continued, the balance may have shifted incrementally until surface temperatures rose beyond the point where water could remain liquid for long. The isotopic traces remain as quiet testimony. They do not confirm blue horizons or rolling tides, but they align with the notion that Venus once passed through a gentler phase. In that distant epoch, under a dimmer sun, and within a complex interplay of clouds and gases, the young planet may have lingered near a threshold, sustaining shallow waters that endured not for moments, but for spans measured in millions of years before conditions moved steadily away from that fragile equilibrium. Between the orbits of Mercury and Earth, a narrow band of space traces a path only slightly nearer to the Sun. Yet that small inward shift alters the arithmetic of light in profound ways. Venus circles at about 0.72 AU, a difference that seems modest when drawn on a diagram, but radiation does not diminish gently with distance. It follows an inverse square law, meaning that a fraction of orbital change reshapes the total energy received. At that position, Venus absorbs nearly twice the solar energy that reaches Earth today, bathing its upper atmosphere in a constant surplus of light. Solar radiation arrives in visible and ultraviolet wavelengths, penetrating clouds, scattering through gases, and warming surfaces that re-emit energy as infrared heat. The balance between what a planet absorbs and what it radiates back to space determines its equilibrium temperature. On Venus, the greater intensity of incoming sunlight meant that any atmosphere present from the earliest epochs had to work harder to shed excess heat. Infrared radiation could escape only if the atmosphere remained sufficiently transparent in certain wavelength windows. Even slight increases in greenhouse gases narrow those windows, trapping warmth that would otherwise drift outward into space. In the youth of the solar system, the sun shone less brightly, softening the contrast between 0.72 AU and Earth's more distant path. Yet the geometry still favored Venus with a persistent advantage in energy input. As solar luminosity gradually increased over hundreds of millions of years, that advantage grew steadily. Climate does not respond in straight lines. It responds through feedbacks. When temperatures rise, evaporation intensifies, increasing water vapor in the atmosphere. Water vapor itself absorbs infrared radiation, amplifying warming. Clouds can either cool by reflecting sunlight or warm by trapping heat, depending on their altitude, thickness, and composition. In a system already receiving abundant radiation, these feedbacks become increasingly sensitive. The concept of radiative equilibrium rests on a fragile interplay between absorption and emission. A planet must radiate as much energy as it receives to maintain stable temperatures. If absorption slightly exceeds emission, heat accumulates. Over time, that accumulation shifts atmospheric chemistry and circulation patterns. On a world positioned closer to its star, the margin for stability narrows. Higher baseline temperatures mean that oceans, if present, would evaporate more readily, increasing atmospheric opacity. Greater opacity reduces the efficiency of infrared cooling, pushing surface conditions further from their original state. Distance also influences the vertical structure of the atmosphere. Enhanced solar heating can drive stronger convection, lofting water vapor and other gases to higher altitudes where ultraviolet radiation is more intense. There, molecular bonds break more easily, altering composition and allowing lighter elements to escape gravitational hold. The cumulative effect of slightly increased solar flux, sustained over geological timescales, becomes more than incremental. It establishes initial conditions that predispose a planet towards certain climatic pathways. None of this required dramatic events at first. A marginally warmer surface, a marginally thicker layer of greenhouse gases, a marginally slower rate of cooling could coexist for long periods without immediate catastrophe. Yet the steady difference in orbital position ensured that Venus always operated closer to thresholds defined by radiation physics. The additional sunlight did not dictate its destiny in isolation, but it set the stage upon which atmospheric processes unfolded. In that narrow corridor of space, only a few tens of millions of kilometers inward, the arithmetic of energy tilted just enough to make equilibrium more delicate, more easily disturbed, and increasingly difficult to restore once displaced. Warmth on a planet is not held by sunlight alone, but by what happens after that light touches ground and sea. When solar radiation reaches a surface, it is absorbed and later released as infrared energy, a longer wavelength glow invisible to human eyes. If nothing stood in its path, much of that heat would slip quietly back into space. Yet, atmospheres are not empty. Certain gases, though transparent to incoming sunlight, interact strongly with outgoing infrared radiation. They absorb it, vibrate at molecular frequencies, and re-emit it in all directions, including back toward the surface. This quiet exchange creates what scientists call the greenhouse effect, a natural planetary blanket woven not from fabric but from physics. Carbon dioxide plays a central role in this process. Its molecular structure allows it to absorb specific bands of infrared radiation, particularly those emitted by a warming surface. When CO2 concentrations increase, the atmosphere becomes more opaque in those bands, narrowing the channels through which heat can escape. Energy remains longer within the lower atmosphere, raising equilibrium temperatures until a new balance between incoming and outgoing radiation is achieved. This mechanism does not require extreme abundance to function. Even trace amounts of greenhouse gases can elevate surface temperatures significantly compared to a world with no atmosphere at all. On Earth, this effect is not an anomaly, but a prerequisite for habitability. Without greenhouse gases, such as carbon dioxide and water vapor, Earth's average surface temperature would rest well below freezing. Liquid water would be scarce, and biological processes as known today would struggle to persist. The greenhouse effect, in its moderate form, stabilizes climate by preventing extreme diurnal swings and by maintaining temperatures compatible with oceans and weather cycles. It is a balancing force, responsive to volcanic outgassing, chemical weathering, and the slow drawdown of carbon into rocks and sediments. The distinction between gentle warming and destabilizing heating lies in feedback strength and atmospheric composition. In a mild regime, increases in temperature can trigger compensating processes. Enhanced weathering may remove carbon dioxide from the atmosphere. Cloud cover might reflect additional sunlight. Oceans may absorb excess heat and dissolved gases. In a runaway scenario, however, warming amplifies itself faster than stabilizing mechanisms can respond. Higher temperatures increase water vapor, which intensifies infrared absorption. If surface water evaporates extensively, the atmosphere thickens with greenhouse gases, reducing its ability to radiate heat efficiently into space. Once a critical threshold is crossed, equilibrium shifts toward ever higher temperatures until surface conditions transform entirely. Early in Venus's history, volcanic activity likely contributed substantial amounts of carbon dioxide to its atmosphere. Young terrestrial planets are geologically active, their interiors releasing gases trapped during formation. On Earth, much of the emitted CO2 becomes incorporated into carbonate minerals through interaction with liquid water and plate tectonics, gradually cycling between atmosphere, ocean, and crust. On Venus, the balance between outgassing and removal would have depended on surface conditions and the presence of stable water reservoirs. If oceans were shallow or transient, the capacity to dissolve and sequester carbon dioxide may have been limited. As volcanic emissions continued, atmospheric concentrations of CO2 could accumulate, enhancing the greenhouse effect beyond moderate bounds. With each incremental increase, the atmosphere's infrared opacity would rise, raising surface temperatures further. If cooling pathways proved insufficient, the natural blanket would thicken into an insulating shroud. The same physical principle that keeps Earth temperate would, under different circumstances, guide Venus toward a far more extreme equilibrium, demonstrating how a mechanism essential for life can, when amplified, reshape an entire planet's climate into something far less forgiving. Among the gases that drift invisibly through a planetary sky, one carries an influence far greater than its fleeting presence might suggest. Water vapor does not linger for geological ages like carbon dioxide, yet, while it remains suspended in air, it absorbs infrared radiation with remarkable efficiency. Its molecular bonds bend and stretch in ways that interact strongly with heat radiating upward from a warmed surface. Even modest concentrations can thicken the thermal fabric of an atmosphere, narrowing the pathways through which energy escapes into space. Unlike carbon dioxide, whose abundance is shaped largely by volcanic release and chemical cycling, water vapor responds directly to temperature. As surface conditions grow warmer, evaporation intensifies. Liquid water transitions more readily into gas, rising from oceans, lakes, or damp ground into the overlying air. This transformation requires energy, drawn from the surface as latent heat. But once the vapor ascends and later condenses, that stored energy is released into higher layers of the atmosphere. The entire process ties surface temperature to atmospheric composition in an intimate exchange. On a world receiving abundant sunlight, incremental warming can therefore amplify itself. Higher temperatures encourage greater evaporation. Greater evaporation increases the concentration of water vapor. Additional vapor strengthens infrared absorption. The atmosphere becomes more opaque to outgoing heat, causing surface temperatures to rise further. This cycle does not require sudden triggers. It unfolds through steady reinforcement, each step building quietly upon the last. Cloud formation complicates the picture. When water vapor condenses, it forms droplets or ice crystals that scatter and reflect sunlight, potentially cooling the surface beneath. At the same time, clouds can absorb and re-emit infrared radiation, contributing to warming. The net effect depends on cloud altitude, thickness, and distribution. On a planet hovering near a thermal threshold, subtle shifts in cloud dynamics may determine whether evaporation slows or accelerates. The interplay between reflection and insolation becomes increasingly delicate as temperatures climb. If surface water reservoirs are extensive, evaporation supplies abundant vapor to the atmosphere. As vapor accumulates, the upper atmosphere grows warmer as well, allowing water molecules to reach greater heights. There, exposed to stronger ultraviolet radiation, they can dissociate into hydrogen and oxygen. Hydrogen, being light, may escape a planet's gravitational hold over time. This gradual loss reduces the total inventory of water available at the surface, diminishing the buffering capacity that liquid oceans provide. The critical feature of water vapor lies in its feedback strength. Carbon dioxide often acts as the initial forcing, setting baseline temperatures through long-lived atmospheric presence. Water vapor responds to that baseline, magnifying its effects. When warming remains modest, the system can settle into a new equilibrium. When warming pushes temperatures beyond certain thresholds, evaporation can outpace stabilizing processes. Oceans shrink, atmospheric opacity increases, infrared cooling becomes progressively less efficient. The feedback loop tightens, reinforcing itself with each increment of temperature rise. On a planet positioned close enough to its star, this amplification may carry climate beyond recovery. As surface water diminishes, the atmosphere transitions from a mixture moderated by liquid reservoirs to one dominated by greenhouse gases without effective sinks. What began as a natural and necessary component of atmospheric balance evolves into a driver of relentless heating. Water vapor, once a transient participant in weather cycles, becomes a turning point gas, capable of shifting a world from conditional stability toward an enduring state defined by its own accumulated warmth. There comes a point in planetary climate when balance ceases to behave like a gentle scale and begins to resemble a tilted plane. A runaway greenhouse does not announce itself with sudden violence. It emerges when outgoing heat can no longer increase fast enough to match the energy absorbed from a star. In ordinary conditions, as a surface warms, it radiates more infrared energy and equilibrium is restored. In a runaway regime, the atmosphere grows so saturated with greenhouse gases that additional warming fails to produce proportional cooling. The system loses its stabilizing response. Climate threshold models describe this transition in terms of radiation limits. As surface temperatures rise, water evaporates in greater quantities, thickening the atmosphere with vapor. Infrared opacity increases, narrowing the spectral windows through which energy escapes. Eventually, a ceiling is reached, in which the planet radiates a nearly fixed maximum amount of heat to space, regardless of further warming at the surface. If incoming solar energy exceeds that limit, temperatures must continue to climb until a new state is achieved, one no longer governed by the presence of stable oceans. On a world already receiving abundant sunlight, gradual brightening of the host star compounds the effect. What begins as incremental warming shifts atmospheric structure. Convection intensifies, carrying moisture higher. Clouds form and dissipate in patterns that may no longer provide net cooling. As the surface warms beyond the boiling point of water at prevailing pressures, liquid reservoirs shrink, seas retreat into steam. Evaporation ceases to be a surface process and becomes planetary in scale. The transformation from ocean to vapor alters more than temperature. Liquid water acts as a thermal buffer, absorbing and redistributing heat. It participates in chemical reactions that sequester carbon dioxide into rocks, moderating atmospheric composition. When oceans evaporate extensively, that buffering capacity disappears. The atmosphere thickens with water vapor, itself a powerful greenhouse gas, amplifying infrared trapping. Surface rocks, no longer shielded by water, heat directly under intensified radiation. As temperatures climb, the distinction between atmosphere and ocean blurs. Steam dominates the lower layers of air. The greenhouse effect strengthens not linearly, but exponentially, because each increment of warming increases vapor concentration, which in turn raises temperature further. The radiative ceiling imposed by atmospheric physics prevents efficient cooling. Heat accumulates until surface conditions stabilize at far higher temperatures than before, beyond the range where liquid water can persist. In the upper atmosphere, water molecules exposed to ultraviolet light dissociate into hydrogen and oxygen. Hydrogen, light and swift, escapes gradually into space. Oxygen may react with surface materials or be lost through other processes. The planet's total water inventory declines irreversibly. Even if temperatures later decrease, the lost hydrogen cannot be reclaimed. Oceans cannot reform without their essential component. The onset of a runaway greenhouse is therefore less a sudden catastrophe than a crossing of a physical boundary. Once atmospheric opacity and solar input surpass critical values, equilibrium shifts toward a new regime defined by persistent heat. The surface no longer cycles between evaporation and condensation. It resides in a state where stable liquid water is absent. What began as a natural greenhouse effect, essential in moderate form, evolves into a self-sustaining engine of warming. The climate system, having passed its threshold, settles into conditions that no longer resemble its earlier phase, and the memory of oceans survives only in isotopic traces carried within a dense and enduring sky. High above the dense lower layers of a warming world, sunlight arrives in a harsher form. Ultraviolet radiation, invisible yet energetic, penetrates the upper atmosphere and encounters molecules carried upward by convection. Among them are water molecules, lifted from evaporating seas into altitudes where air grows thin and exposure intensifies. At these heights, ultraviolet photons possess enough energy to break chemical bonds, splitting water into hydrogen and oxygen in a process known as photodissociation. Once separated, the fate of each fragment diverges. Oxygen, heavier and more chemically reactive, tends to linger. It may recombine into O2, react with surface minerals, or participate in other atmospheric chemistry. Hydrogen behaves differently. As the lightest element, it moves swiftly through the upper atmosphere. If it acquires sufficient kinetic energy, either from thermal motion or interactions with solar wind, it can exceed the planet's escape velocity. Gradually, atom by atom, hydrogen drifts outward into space. This escape does not occur as a sudden exodus, but as a persistent leakage, sustained over millions of years. As long as water vapor continues to rise and ultraviolet radiation continues to break it apart, hydrogen loss proceeds. Each escaping atom represents a fraction of a former ocean. Because water consists of two hydrogen atoms for every oxygen atom, the depletion of hydrogen steadily reduces the total inventory of water available to the planet. Clues to this vanished abundance remain in isotopic ratios measured decades later. Instruments aboard the Venus Express spacecraft analyzed the composition of Venus's atmosphere and detected a striking enrichment of deuterium relative to ordinary hydrogen. Deuterium, a heavier isotope of hydrogen containing an additional neutron, is less likely to escape a planet's gravity due to its greater mass. As lighter hydrogen atoms preferentially drift away, deuterium accumulates in proportion. The elevated deuterium to hydrogen ratio, observed at Venus, suggests that immense quantities of lighter hydrogen were lost in the distant past, consistent with the evaporation and subsequent photodissociation of significant water reservoirs. As oceans thin and vapor dominates, the cycle accelerates. More water in the atmosphere means more molecules available for ultraviolet breakup. With declining surface reservoirs, the buffering effects of liquid water disappear. Chemical weathering that once locked carbon dioxide into rocks diminishes. The climate stabilizes not toward cool recovery, but toward a new equilibrium defined by dryness and heat. The loss of hydrogen carries a finality rooted in physics. Once hydrogen escapes into interplanetary space, it is not readily reclaimed. Unlike heavier gases that might be replenished through volcanic outgassing, hydrogen requires a source of water or other hydrogen-bearing compounds within the planet. If those reservoirs have already been depleted, there is no mechanism to rebuild oceans on a planetary scale. Delivery by later cometary impacts would be minor compared to the vast quantities once present, and any new water introduced would again be vulnerable to evaporation and photodissociation under prevailing conditions. Over time, what may once have been seas become memory, recorded only in atmospheric chemistry. Oxygen left behind reacts with surface materials or is lost through additional escape processes, leaving an atmosphere dominated by other gases. The disappearance of oceans is therefore not merely the evaporation of liquid into steam, it is the progressive dismantling of a planet's water inventory at the atomic level. Through ultraviolet light and gravitational escape, a world can relinquish its hydrogen until no stable body of liquid water can return, sealing its transformation into a dry and enduring state. Rock and water share a quiet conversation on temperate worlds. When rain falls through air containing carbon dioxide, a small portion of that gas dissolves into droplets, forming a weak carbonic acid. As the water moves across continents and into basins, it reacts with silicate minerals, breaking them down and carrying dissolved ions toward the sea. Over long stretches of time, these reactions lock carbon into carbonate rocks, storing it within crustal layers. Plate tectonics later returns some of this carbon to the atmosphere through volcanic outgassing, but the exchange unfolds gradually, regulated by temperature, rainfall, and the steady presence of liquid water. This cycle moderates atmospheric composition, preventing carbon dioxide from accumulating unchecked. On a planet where oceans vanish, that conversation falls silent, without expansive bodies of liquid water to dissolve carbon dioxide. The primary sink for atmospheric CO2 disappears. Rain cannot fall from a sky devoid of condensation. Rivers cannot transport dissolved carbon to sediments. Carbonate rocks cannot form in the same manner. Volcanic outgassing, however, does not cease simply because surface water has been lost. The interior of a rocky planet continues to release carbon dioxide through fissures and eruptions, adding gas to an atmosphere that no longer has an efficient pathway for removal. As this imbalance persists, atmospheric carbon dioxide builds steadily. Each eruption contributes additional molecules, and without a buffering ocean or active weathering cycle to counterbalance emissions, concentrations rise. The greenhouse effect strengthens correspondingly, enhancing infrared absorption and sustaining high surface temperatures. Over millions of years, the atmosphere can become dominated by carbon dioxide, not through a single cataclysm, but through the absence of regulation. On Venus, measurements reveal that carbon dioxide composes about 96% of the present atmosphere. This dominance reflects the cumulative outcome of prolonged outgassing, combined with the loss of liquid water that might have sequestered carbon into rocks. The planet's crust, lacking mobile tectonic plates similar to Earth's, offers limited means of recycling carbon into the mantle in a balanced, ongoing manner. Instead of a dynamic exchange between surface and interior, the atmosphere becomes a vast reservoir for volcanic emissions. As carbon dioxide accumulates, surface pressure increases dramatically. Pressure is a simple consequence of the weight of overlying air. With a thick column of CO2 extending upward for many kilometers, the force exerted at the surface intensifies. On Venus, this pressure exceeds 90 times that at Earth's sea level, comparable to the conditions found nearly 1 kilometer beneath Earth's oceans. Under such compression, gases behave differently, and heat transfer processes shift subtly. The dense atmosphere stores and transports energy with great efficiency, contributing to remarkably uniform surface temperatures across latitudes and between day and night. The carbon dioxide trap is therefore not solely about temperature, it is about permanence. Once oceans disappear and tectonic cycling remains limited, carbon dioxide lacks a pathway back into long term geological storage at a rate sufficient to restore balance. The atmosphere thickens, the greenhouse effect intensifies, and surface pressure climbs. What was once a potential participant in a moderated cycle becomes the dominant constituent of a self reinforcing system. In the absence of liquid water and active recycling, carbon dioxide settles into its role as the primary architect of a dense, enduring sky pressing heavily upon the surface below. Deep beneath a planet's surface, far below crust and mantle, motion can generate an invisible architecture that stretches outward into space. Within Earth, a molten outer core composed largely of iron and nickel circulates slowly around a solid inner core. As this electrically conductive fluid moves, it creates currents. Those currents produce a magnetic field that extends far beyond the atmosphere, forming a protective region known as the magnetosphere. Though unseen, it shapes the flow of charged particles streaming from the sun, guiding them along curved paths and deflecting much of their energy away from the atmosphere below. This magnetic field is sustained by heat escaping from Earth's interior, which drives convection in the outer core. The rotation of the planet organizes that motion into large-scale patterns, reinforcing the field through what geophysicists call a dynamo process. Over millions of years, the field has shifted, weakened, and even reversed polarity, yet it has remained a persistent feature of Earth's structure. Its presence does not eliminate interaction with solar radiation, but it reduces the direct impact of high-energy charged particles on the upper atmosphere. Venus, similar in size and bulk composition, likely possesses an iron-rich core as well. Yet observations indicate that it lacks a strong global magnetic field comparable to Earth's. Spacecraft measurements suggest only weak, localized magnetic signatures induced by interaction with the solar wind rather than generated internally. The absence of a robust dynamo may stem from differences in core cooling rates, mantle convection, or rotational dynamics. Without sufficient heat flow to drive vigorous motion in a liquid outer core, the mechanism required to sustain a global magnetic field cannot operate effectively. In the absence of such shielding, the solar wind interacts more directly with the upper layers of the atmosphere. The solar wind is a continuous stream of charged particles, primarily protons and electrons, emitted by the sun. When these particles encounter a planet without a strong magnetosphere, they can erode the atmosphere through processes such as sputtering and ion pickup. At high altitudes, atmospheric gases become ionized by ultraviolet radiation. The solar wind can then impart energy to these ions, accelerating some of them to velocities that allow escape into space. On Earth, the magnetosphere channels many of these particles toward the polar regions, where they produce auroras rather than widespread atmospheric loss. The magnetic field thus acts as a buffer, moderating the rate at which lighter atmospheric constituents are stripped away. While Earth still loses small amounts of hydrogen and other light elements, the process unfolds slowly compared to what might occur without magnetic protection. On Venus, the interaction between solar wind and atmosphere creates an induced magnetotail and a bow shock, but these structures arise from the atmosphere itself rather than from an internally generated field. This configuration offers less comprehensive shielding. Over long periods, enhanced escape of lighter elements may contribute to atmospheric evolution, especially when combined with photodissociation of water and other processes already underway. Magnetism, therefore, represents more than a geophysical curiosity. It influences how a planet exchanges matter and energy with its star. A strong magnetic field can help preserve volatile components by reducing direct erosion from charged particles. In its absence, atmospheric constituents are more exposed to solar forces. The contrast between Earth's enduring magnetosphere and Venus's weak induced field adds another layer to their divergence, illustrating how internal dynamics shape not only a planet's geology, but also the stability of the air that surrounds it. Above the surface of Venus stretches a layered ceiling so thick that it erases any direct view of the ground below. Long before spacecraft descended through it, telescopes saw only a pale, uniform disk, bright and featureless. That brightness is not the glow of exposed terrain, but the reflection of sunlight from a continuous deck of clouds suspended high in the atmosphere. The origin of those clouds begins with volcanic gases rising from the interior. Among the gases released through eruptions and fissures is sulfur dioxide, a compound that accumulates readily in a carbon dioxide dominated atmosphere. Carried upward by convection, sulfur dioxide encounters trace amounts of water vapor lingering in the upper layers. Under the influence of ultraviolet radiation, chemical reactions convert these ingredients into sulfuric acid. Tiny droplets of this acid condense around microscopic particles, forming dense clouds that wrap the planet in a persistent veil. These clouds are not thin wisps drifting across open sky. They form multiple strata extending from roughly 45 to 70 kilometers above the surface. Within this altitude range, temperatures and pressures allow sulfuric acid droplets to remain stable, circulating in global wind patterns. The cloud layers are so optically thick that only a small fraction of incoming sunlight penetrates through to the ground. Most visible light is scattered or reflected back into space before it can illuminate the surface. This high reflectivity gives Venus an albedo of about 0.75, meaning it reflects roughly 3/4 of the sunlight that strikes it. From a distance, this makes Venus one of the brightest objects in Earth's sky, often outshining every star. The cloud tops gleam in sunlight, creating the impression of a luminous world. Yet brightness does not equate to coolness. While much incoming visible light is reflected, the energy that is absorbed, combined with the powerful greenhouse effect of the dense atmosphere below, becomes trapped efficiently. Sunlight that filters through the clouds reaches the lower atmosphere already scattered and diffused. It warms the surface, and the thick carbon dioxide air near the ground. The heated surface then emits infrared radiation upward. Unlike visible light, infrared radiation interacts strongly with carbon dioxide and other greenhouse gases. The dense atmosphere absorbs this outgoing heat and re emits it in all directions, including back toward the surface. The clouds themselves, though reflective in visible wavelengths, also contribute to infrared trapping at certain frequencies, reinforcing the retention of heat. The result is a striking paradox. A planet wrapped in brilliant clouds, reflecting most of the sunlight it receives, maintains surface temperatures hot enough to soften metals. The reflective canopy limits direct solar heating at the ground, yet the atmosphere's composition ensures that once energy enters the system, it escapes only slowly. High albedo and extreme heat coexist because reflectivity operates primarily in the visible spectrum, while greenhouse trapping dominates in the infrared. Within the cloud layers, winds move at tremendous speeds, circulating the upper atmosphere far more rapidly than the surface rotates. Beneath them, the lower atmosphere remains dense and sluggish, insulated by the weight of the gases above. The surface lies in perpetual twilight, illuminated by a dim, orange filtered light that never breaks into clear sky. In this world of clouds, brightness belongs to the upper atmosphere, while below, heat persists quietly under a shroud that both shields and confines. Time passes differently on Venus. The planet turns so slowly that a single rotation takes 243 Earth days, longer than the time it needs to complete one orbit around the Sun. Its surface drifts through light and shadow at a pace almost imperceptible, as though the world itself hesitates in motion. Yet high above that languid rotation, the atmosphere refuses to remain still. At altitudes near the cloud tops, the air races around the planet in a phenomenon known as superrotation. While the solid surface turns with immense patience, the upper atmosphere circles the globe in roughly 4 Earth days. Winds in these layers can reach speeds of 360 kilometers per hour, creating a stark contrast between the quiet ground below and the rapid circulation overhead. This difference is not a simple breeze over terrain. It is an atmospheric system moving many times faster than the body it surrounds. The origin of this superrotation lies in the complex exchange of momentum between solar heating, planetary rotation, and atmospheric waves. Even with slow surface movement, sunlight warms the day side more than the night side, driving temperature gradients that initiate large-scale circulation patterns. Air heated near the equator rises and flows toward higher latitudes before descending again, forming vast cells that span hemispheres. Within these cells, momentum can be transferred upward, accelerating the upper atmosphere beyond the speed of the surface itself. Thermal tides, generated by periodic heating as the planet turns, also contribute. These tides are not oceanic, but atmospheric, waves of pressure that propagate through dense air. As they interact with planetary scale waves and with the underlying topography, they redistribute angular momentum, gradually spinning up the cloud level winds. The dense carbon dioxide atmosphere provides ample mass to sustain these motions, allowing energy to be stored and transported efficiently. Despite the rapid winds aloft, the lower atmosphere remains comparatively sluggish. Near the surface, the immense pressure and density of the air dampen horizontal movement. Winds at ground level are often gentle, measured in only a few kilometers per hour, even though the air itself is heavy enough to exert tremendous force. The result is a layered dynamic, calm at the base and swift above, each stratum behaving according to its own balance of forces. Superrotation plays a crucial role in distributing heat. With a day longer than a year, one hemisphere of Venus could, in theory, bake under prolonged sunlight while the other cools in extended darkness. Instead, the fast moving upper atmosphere carries energy around the planet, smoothing temperature differences. Measurements show that surface temperatures remain remarkably uniform from equator to poles and from day to night. The dense atmosphere and its rapid circulation prevent extreme contrasts, maintaining a global climate that is consistently hot rather than unevenly so. This coupling of slow planetary spin and swift atmospheric motion creates a world where time and wind move on different scales. The ground rotates with measured persistence, while the clouds sweep overhead in continuous motion. Together, they form a climate system that redistributes energy across the entire globe, ensuring that heat, once trapped within the thick air, is shared widely rather than confined to a single hemisphere. On Venus, sunrise would come slowly, almost imperceptibly, as though the horizon itself were reluctant to move. The planet completes one rotation on its axis every 243 Earth days, an interval longer than the 225 Earth days it takes to circle the Sun. In orbital terms, a year passes more quickly than a single spin. This unusual rhythm shapes not only the passage of light across the surface, but the deeper mechanics of atmosphere and interior. Adding to this peculiarity is the direction of rotation. Venus turns in a retrograde motion, opposite to the direction of most planets in the solar system. If viewed from above, the Sun's north pole, Venus spins clockwise, while Earth and most others rotate counterclockwise. As a result, on Venus, the Sun would appear to rise in the west and set in the east. The reasons for this reversal remain subjects of scientific modeling rather than direct observation, yet several plausible pathways have been proposed. One possibility involves massive impacts during the planet's early formation. In the crowded inner solar system, collisions between protoplanets were common. A sufficiently large impact, striking at an oblique angle, could have altered Venus's angular momentum, slowing its original spin or even reversing it. Another explanation considers tidal interactions between Venus and the Sun. Over immense spans of time, gravitational forces can exert torque on a planet's rotation, particularly if atmospheric tides contribute additional momentum exchange. Computer simulations suggest that a combination of atmospheric thermal tides and solar gravitational effects might gradually break and reverse rotation under certain conditions. Regardless of its origin, the slow and retrograde spin has profound consequences for climate. On a rapidly rotating planet like Earth, the alternation of day and night distributes solar heating across the globe within hours. Temperature differences between hemispheres are moderated by both rotation and atmospheric circulation. On Venus, with daylight lasting for months at a time in a single location, one might expect extreme contrasts between the sunlit and dark sides. Yet, observations reveal a surface temperature that varies little between regions, remaining remarkably uniform. This stability arises from the dense atmosphere and its dynamic circulation. Even though the solid planet rotates slowly, the upper atmosphere, as previously described, moves swiftly, transporting heat around the globe. The prolonged exposure of one hemisphere to sunlight does not result in runaway heating in that region alone, because energy is redistributed before it can accumulate unevenly. The thickness of the atmosphere also acts as a thermal reservoir, storing and diffusing heat over time. Slow rotation influences the development of atmospheric waves and circulation cells, With weaker Coriolis forces compared to faster spinning planets, large scale circulation patterns can extend across vast latitudinal ranges. This configuration may support the superrotation observed at cloud level, reinforcing the rapid movement of air relative to the surface. The interplay between sluggish ground rotation and vigorous atmospheric motion creates a system in which heat is shared efficiently despite the planet's unusual day length. Thus, a day longer than a year is not merely a curiosity of celestial mechanics, it is a structural feature that shapes the climate architecture of Venus. The backward, deliberate turn of the planet interacts with solar tides, atmospheric dynamics, and internal history, producing a world where time unfolds differently, yet where temperature remains consistently high across every longitude. Descent toward the surface of Venus is not a passage into shadow, but into density. As altitude decreases, the atmosphere thickens steadily, transitioning from turbulent cloud layers into a heavy, opaque expanse of carbon dioxide. Light filtering down from above becomes dim and amber, scattered so thoroughly that no clear sky is visible. By the time the ground comes into view, the air itself feels less like wind and more like weight. At the surface, temperatures hover around 465 degrees Celsius, remaining astonishingly consistent across latitudes and longitudes. Measurements from orbiters and landers reveal that equatorial regions and polar areas differ only slightly, and the contrast between day and night is minimal. Even though Venus rotates slowly, allowing extended periods of daylight and darkness at any given location, the dense atmosphere redistributes heat so effectively that nighttime cooling is almost non existent. The planet does not experience the sharp thermal swings common on airless bodies. Instead, it maintains a nearly uniform, furnace like state, uninterrupted by the passage of its long days. The reason for this uniformity lies in the mass and composition of the atmosphere. Carbon dioxide, compressed under its own weight, forms a thick blanket that traps infrared radiation and transports heat through convection and circulation. The lower atmosphere behaves almost like a fluid ocean of gas, carrying energy laterally as well as vertically. With such density, even slow winds can move substantial amounts of thermal energy, preventing localized cooling. The surface remains immersed in a constant bath of heat, regardless of solar illumination at that moment. Pressure at the surface reaches more than 90 times that of Earth's sea level atmosphere, comparable to conditions nearly 1 kilometer beneath Earth's oceans. Under this compression, gases become dense enough to exert significant force on any structure. The combination of high temperature and immense pressure creates an environment that challenges both materials and electronics. Metals soften, polymers degrade rapidly, circuits designed for terrestrial conditions fail as heat penetrates housings and overwhelms cooling systems. The Soviet Venera landers, which briefly transmitted data from the surface, provide direct testimony to these conditions. Encased in specially reinforced shells and equipped with cooling systems intended to delay the inevitable, they survived for minutes to a little over 2 hours before succumbing. As internal temperatures rose, electronic components drifted beyond operational limits. Structural elements endured crushing forces, yet even robust engineering could only postpone failure in such an extreme setting. Sound behaves differently in this dense medium as well. The thick air transmits vibrations efficiently, altering how pressure waves propagate. If one could stand there, the sensation would not resemble standing in a desert or on a volcanic plain on Earth. It would feel as though submerged, within a superheated sea of gas, every surface pressed upon by relentless atmospheric weight. There is no respite in darkness, no cooling breeze at twilight. The surface of Venus exists in a steady state, shaped by atmospheric physics rather than by daily cycles. Heat is shared globally, pressure remains constant, and the environment tests the limits of mechanical endurance. In this crushing reality, the planet's transformation becomes tangible, not only in chemical composition or orbital mechanics, but in the direct physical experience of standing beneath a sky that presses downward with unyielding force. For centuries, Venus had been a bright, featureless presence in the sky, its surface concealed behind reflective clouds. The first true glimpses of what lay beneath did not come from telescopes, but from machines built to endure conditions no human could survive. During the 20th century, the Soviet Union launched a series of spacecraft known as the Venera missions, designed to descend through the dense atmosphere and transmit data from the surface before being overcome. The early attempts ended in silence, crushed or overheated before reaching the ground. Engineers refined their designs with each launch, strengthening pressure vessels, adding insulation, and developing cooling systems capable of delaying the inevitable rise in internal temperature. By the time Venera 7 reached Venus in 1970, it became the first spacecraft to transmit data from the surface of another planet. It survived for just over 20 minutes after landing, sending back measurements of temperature and pressure that confirmed the extreme conditions long predicted by theory. Later missions extended that fragile window. Venera 9 and 10, arriving in 1975, returned the first images from the surface. The photographs revealed a landscape unlike the imagined oceans or jungles of earlier speculation. Instead, the terrain appeared rocky and fractured, scattered with angular stones resting on a flat plain. The sky, filtered through the thick atmosphere, cast a muted orange light over everything. The horizon seemed close, blurred by the density of the air. Venera 13 and 14, launched in the early 1980s, provided the most detailed data. Venera 13 survived for 127 minutes, transmitting panoramic images and conducting chemical analyses of the soil. Its cameras captured slabs of rock and granular regolith that resembled basalt, suggesting volcanic origins. The lander's instruments indicated a surface composed largely of igneous material, consistent with widespread volcanic resurfacing inferred from radar observations. The rocks appeared fractured, perhaps shaped by thermal stress or past tectonic activity. These spacecraft did not explore vast distances. They landed, unfolded, and began transmitting immediately, racing against time as internal temperatures climbed. Cooling systems relied on pre-chilled components and limited insulation. Once exposed to the ambient 465 degrees Celsius environment and crushing pressure exceeding 90 times that of Earth's sea level, heat seeped inward steadily. Electronics degraded. Signals weakened. Eventually, transmission ceased as circuits failed. Despite their brief lifespans, the Venera landers transformed understanding of Venus. They confirmed that the surface was solid, rocky, and geologically complex. They measured atmospheric composition near the ground, verifying the dominance of carbon dioxide and the presence of trace gases. They recorded wind speeds and light levels, revealing a dim but steady illumination. Even the sound of the landers settling onto the surface, transmitted through the dense air, hinted at the texture of the terrain. The images they returned remain grainy by modern standards, yet they carry a quiet gravity. They show not a chaotic inferno, but a stark, enduring landscape shaped by heat and pressure over immense spans of time. Each mission functioned as a brief visitor, arriving, observing, and then succumbing to the environment it sought to study. In those minutes and hours, humanity obtained its first direct encounter with the ground of Earth's twin, replacing speculation with tangible evidence of a world both familiar in its rocky composition and profoundly altered in its climate. Long after the brief transmissions from the Venera landers faded, a different kind of exploration began from orbit. Instead of descending through the atmosphere, spacecraft turned to radar, a method capable of penetrating the dense cloud layers that conceal the surface from visible light. In the early 1990s, NASA's Magellan spacecraft entered orbit around Venus and began mapping the planet with synthetic aperture radar, sending pulses downward and measuring the echoes that returned. Over several years, it charted nearly the entire surface in remarkable detail, revealing a landscape shaped overwhelmingly by volcanic processes. What emerged from the radar images was not a world dominated by impact craters or fragmented continents, but one covered in vast volcanic plains. These plains stretch across enormous regions, appearing smooth at large scales, their surfaces solidified from extensive flows of lava that once spread outward and cooled. The relative scarcity of impact craters suggests that much of the terrain is geologically young on planetary timescales, resurfaced by widespread volcanic activity that buried older features beneath layers of basalt. Rising above these plains are thousands of volcanoes, ranging from small domes to immense shield structures spanning hundreds of kilometers. Shield volcanoes form when low viscosity lava flows outward in thin sheets, building broad, gently sloping mountains over time. On Venus, some of these structures rival or exceed the largest volcanoes on Earth in scale. Their outlines, traced in radar reflections, reveal calderas, lava channels, and collapsed summits. In addition to classical shields, the surface displays unique formations such as coronae, circular features believed to result from mantle upwellings that deform the crust from below. The absence of plate tectonics, as previously considered, means that heat from the interior may escape differently than on Earth. Instead of being released gradually along spreading ridges and subduction zones, internal energy on Venus appears to accumulate beneath a stagnant crust until it is discharged through extensive volcanic outpourings. Magellan's maps show evidence of enormous lava flows that traveled hundreds of kilometers, suggesting eruptions of considerable magnitude. In recent years, further spacecraft observations have renewed interest in the possibility that Venus remains volcanically active today. Data from the European Space Agency's Venus Express mission hinted at transient increases in sulfur dioxide concentrations in the upper atmosphere, potentially linked to volcanic outgassing. Infrared measurements have identified localized thermal anomalies that could indicate relatively recent lava flows. More recently, reanalysis of Magellan radar images has suggested surface changes between mapping cycles, including alterations in the shape of a volcanic vent consistent with an eruption during the mission's lifetime. These findings remain subjects of careful scrutiny and debate. The harsh surface environment complicates direct confirmation, and alternative explanations must be considered. Yet the growing body of evidence suggests that Venus may not be a geologically dormant world. Instead, it could be a planet where internal heat continues to find pathways to the surface, reshaping terrain in ways that radar can detect from orbit. Through radar vision, the image of Venus has shifted from a uniform, hidden sphere to a planet defined by fire from within. Beneath the clouds, Vast plains and towering shields testify to a history dominated by molten rock, and perhaps to a present still marked by intermittent eruptions that quietly renew the surface under an unchanging sky. Across most airless worlds in the inner solar system, time leaves a visible record. The Moon and Mercury bear the scars of billions of years of impacts, their surfaces densely marked by craters layered upon craters. Each collision remains etched into stone, preserved in the absence of erosion or tectonic renewal. When radar maps of Venus were first assembled, scientists expected to see a similar history written across its plains. Instead, they found something strikingly different. Venus possesses far fewer impact craters than would be anticipated for a planet of its age. The craters that do exist are distributed relatively evenly across the globe, with little sign of heavily cratered, ancient regions juxtaposed against smoother, younger terrains. Most of the craters appear similar in age, suggesting that the visible surface formed within a comparatively narrow window of geological time. Estimates place this widespread, resurfacing event roughly between 300 and 700 million years ago, a span brief on planetary scales. The pattern implies that much of the earlier record was erased. Rather than experiencing gradual, localized volcanic activity that slowly modifies isolated areas, Venus appears to have undergone an episode of extensive renewal. Vast regions may have been flooded with lava, burying older craters and leveling pre-existing landscapes. Radar images reveal expansive plains that seem to have solidified from enormous outpourings of molten rock, smoothing the crust across continental scales. One hypothesis proposes a form of catastrophic crust recycling unique to a planet without active plate tectonics. On Earth, heat from the interior escapes through moving plates, subduction zones, and spreading ridges, allowing gradual renewal of the surface. Venus, lacking such mobile plates, may trap internal heat beneath a rigid outer shell. Over hundreds of millions of years, thermal energy could accumulate within the mantle, increasing pressure beneath the crust. Eventually, the stagnant lid might weaken or fracture extensively, releasing stored heat through widespread volcanic eruptions. In this scenario, the planet's outer layer would not recycle continuously, but episodically. A global or near global pulse of volcanism could resurface immense areas in a relatively short geological interval. Lava would inundate plains, fill basins, and obscure older impact structures. Once the heat dissipated and the crust thickened again, volcanic activity might subside into a quieter phase, leaving behind a comparatively young and uniform surface. The evidence supporting this interpretation lies in crater statistics and the apparent age clustering of surface features. If Venus had been resurfaced gradually and randomly over billions of years, a wider range of crater densities would likely be observed. Instead, the limited number of craters and their consistent distribution suggest a resetting of the visible crust within that 300 to 700 million year window. Such a global resurfacing event would have reshaped not only topography, but also atmospheric composition. Large-scale volcanism releases significant amounts of gases, including carbon dioxide and sulfur compounds, into the atmosphere. A surge of outgassing during this period could have reinforced the already dense greenhouse conditions, further stabilizing the planet in its extreme climate state. The concept of a planetary surface being reset in this manner alters the way Venus is understood. Rather than preserving a continuous archive of its earliest epochs, the planet may conceal much of its deeper past beneath layers of relatively recent lava. What is visible today could represent the aftermath of a profound internal episode, a moment when accumulated heat forced the crust to renew itself on a global scale, leaving a surface that appears geologically young despite the ancient origin of the world beneath it. On Earth, the outer shell of the planet is not a single unbroken skin, but a mosaic of moving plates drifting atop a softer mantle. These tectonic plates slide past one another, collide, and separate in a slow choreography powered by internal heat. At mid ocean ridges, new crust forms as magma rises and cools. At subduction zones, older crust descends back into the mantle, carrying with it sediments, water, and carbon locked in minerals. This motion reshapes continents, builds mountain ranges, and, over immense spans of time, regulates the chemistry of the atmosphere. Carbon plays a central role in this cycle. Carbon dioxide dissolves in rainwater, reacts with exposed rock, and is transported to the oceans where it becomes incorporated into carbonate sediments. Through subduction, some of this carbon rich material is drawn downward into the mantle. Later, volcanic eruptions return a portion of it to the atmosphere. This exchange does not occur quickly, yet it establishes a long term balance. When atmospheric carbon dioxide rises, increased temperatures and rainfall accelerate weathering, enhancing removal. When levels fall, weathering slows and volcanic input gradually restores concentrations. The planet maintains a dynamic equilibrium through constant movement. Venus appears to lack this restless surface mobility. Radar mapping and gravity measurements show no clear evidence of global plate boundaries analogous to Earth's ridges and trenches. Instead, the crust of Venus behaves as a stagnant lid, a rigid outer shell that resists continuous fragmentation. Without widespread subduction, the mechanisms that cycle carbon and water between surface and interior operate very differently. The crust remains largely intact over vast regions until disrupted by volcanic or tectonic events that do not resemble plate-driven processes. In such a system, heat generated within the mantle by radioactive decay and residual formation energy has fewer pathways to escape. On Earth, plate motion facilitates efficient heat transfer through spreading centers and subduction zones. On Venus, internal heat may accumulate beneath the stagnant lid, gradually increasing thermal stress. Over time, buoyant plumes of hot mantle material can rise, deforming the crust from below and producing volcanic structures such as coronae and large shield volcanoes. Without steady recycling, the release of internal energy may occur episodically. Instead of continuous, moderate, volcanic outgassing distributed along plate boundaries, Venus could experience intervals of intensified activity, separated by quieter phases. As heat builds beneath the crust, the mechanical strength of the lid may weaken until fractures propagate across extensive areas. Large volumes of magma can then reach the surface, flooding plains and releasing significant quantities of gases into the atmosphere. This pattern aligns with the evidence for widespread resurfacing discussed earlier. A stagnant lid regime does not imply geological inactivity, rather, it suggests a different tempo. The crust acts as a barrier, containing heat until thresholds are crossed. When release comes, it may be broad and transformative, resetting large portions of the surface. Afterward, the lid thickens again, and the cycle of gradual heating resumes beneath it. The absence of plate tectonics therefore shapes both the geology and climate of Venus. Without subduction to sequester carbon or continuous motion to dissipate heat evenly, the planet evolves along a path distinct from Earth's. Internal energy accumulates, atmospheric gases persist, and the crust renews itself in pulses rather than through steady motion. In this quieter but more episodic system, the relationship between interior and surface is defined not by constant drift, but by long intervals of tension, followed by expansive release. Within the thick layers high above Venus's surface, light sometimes appears where no sunlight reaches directly. It does not arrive as steady illumination, but as brief, localized flashes detected by orbiting instruments and passing probes. These signals, subtle and intermittent, suggest electrical activity unfolding inside the sulfuric acid cloud decks that encircle the planet. Evidence for lightning on Venus has accumulated gradually. Soviet landers recorded low-frequency radio bursts during their descent, signatures that resembled the electromagnetic pulses produced by lightning on Earth. Decades later, orbiters such as Venus Express detected Whistler mode waves in the ionosphere, disturbances that can be generated by electrical discharges within an atmosphere. While interpretation remains careful and ongoing, the convergence of radio measurements and optical hints points toward the presence of electrical storms embedded in the cloud layers. The environment in which this lightning would form differs significantly from terrestrial storms. On Earth, lightning arises within towering cumulonimbus clouds composed primarily of water droplets and ice crystals. Strong updrafts separate electric charges, creating regions of positive and negative potential. When the electric field becomes intense enough, a discharge occurs, equalizing the imbalance in a bright, branching flash. Rain, hail, and vertical convection play essential roles in this process. On Venus, the clouds are composed not of water but of concentrated sulfuric acid droplets suspended in a dense carbon dioxide atmosphere. The vertical structure of the atmosphere is distinct, with cloud layers confined to altitudes where temperatures and pressures allow acid condensation. Although convection exists, it operates within a different chemical and thermal regime. The droplets themselves carry charge, and collisions between them, driven by turbulence and atmospheric waves, may lead to charge separation. If sufficient electric potential builds between regions of differing charge, a discharge could occur within or between cloud layers. The characteristics of such lightning would likely diverge from familiar terrestrial patterns. In the dense Venusian atmosphere, electrical breakdown thresholds differ, and the propagation of a discharge channel may follow altered pathways. The absence of liquid water at the surface eliminates the grounding processes common on Earth. Discharges may remain confined within the cloud deck rather than extending downward to the ground. Optical flashes, if present, could be muted by the thick cloud layers and scattering effects, making direct observation from orbit challenging. Electrical activity in the clouds has implications beyond momentary flashes. Lightning can drive chemical reactions by providing energy to break molecular bonds, potentially altering the composition of the surrounding atmosphere. On Earth, lightning contributes to the formation of nitrogen oxides. On Venus, electrical discharges within sulfuric acid clouds could influence sulfur chemistry, affecting the distribution of sulfur dioxide and related compounds. Though the surface below remains shielded from direct view, the upper atmosphere reveals itself through these transient signals. Lightning, if confirmed as a persistent feature, would add another layer of dynamism to a planet often described only in terms of static heat and pressure. Within the reflective clouds, amid winds that circle the globe, electrical storms may flicker unseen from the ground, illuminating the chemistry and motion of an atmosphere that remains active despite the unchanging conditions far beneath it. Far above the crushing surface, At altitudes between roughly 50 and 60 kilometers, the atmosphere of Venus enters a different regime. Pressure decreases to values closer to those at Earth's surface, and temperatures fall into a range that, in isolation, would not immediately preclude the stability of complex molecules. In this suspended layer, droplets of sulfuric acid drift within carbon dioxide gas, carried by winds that circle the planet. Though the ground below remains hostile, this middle atmosphere presents conditions that, at least in terms of temperature and pressure, appear more temperate. It was within this context that renewed interest in possible aerial habitability emerged. In 2020, a team of researchers reported the detection of phosphine in the Venusian atmosphere using observations from ground-based radio telescopes and the Atacama Large Millimeter Array. On Earth, phosphine is associated primarily with biological processes or with industrial production. It is unstable in oxygen-rich environments and tends to break down rapidly under ultraviolet radiation. Its reported presence in the clouds of Venus, if confirmed, would suggest an active source replenishing it. The announcement prompted widespread attention, not because it confirmed life, but because it introduced a chemical puzzle. Known abiotic processes under Venusian conditions struggled to account for the reported concentration levels. The idea that microbial life might persist within cloud droplets, metabolizing chemical energy and producing phosphine as a byproduct, was proposed as one possible explanation. Such organisms, if they existed, would inhabit acidic aerosols, relying on protective adaptations unknown on Earth. Yet, scientific claims require careful verification. Subsequent analyses re-examined the spectral data, refining calibration techniques and reassessing potential sources of error. Some studies suggested that the original signal might have been overestimated or misinterpreted, potentially attributable to sulfur dioxide or instrumental artifacts. Additional observations yielded lower phosphine concentrations or failed to detect it altogether. The debate shifted from biological speculation to questions of measurement sensitivity and atmospheric modeling. At present, no consensus supports the confirmed presence of phosphine at levels demanding extraordinary explanation. The episode illustrates the complexity of remote sensing in a dense and chemically active atmosphere. Minor variations in assumed temperature profiles, cloud opacity, or line broadening can influence spectral interpretation. The chemistry of Venus's clouds remains incompletely understood, and laboratory experiments under relevant conditions continue to explore possible non-biological pathways for phosphine formation. Beyond phosphine, the broader question of life in the clouds remains open in principle but unproven in evidence. The acidity of the droplets is extreme, with concentrations of sulfuric acid far exceeding those tolerated by known terrestrial extremophiles. Water activity within these droplets appears low, limiting the availability of liquid water in a biologically accessible form. Ultraviolet radiation, though attenuated by overlying clouds, still penetrates at levels that challenge molecular stability. No direct detection of living organisms has been made. No metabolic byproducts have been confirmed. The notion of aerial microbes persists as a hypothesis grounded in specific atmospheric niches rather than in observation. In the layered skies of Venus, temperatures may briefly resemble those of Earth, yet chemistry and environment impose constraints that remain formidable. For now, the clouds hold questions rather than answers, suspended within an atmosphere that invites careful study without yielding definitive proof of life. Placed side by side in the mind, Earth and Venus appear at first as variations on a single design. Their diameters differ only modestly. Their masses lie within the same range, and both formed from the same inner reservoir of rock and metal. Yet, when their present conditions are compared in detail, the divergence becomes profound, expressed not in subtle gradients, but in distinct physical regimes. The atmosphere of Earth is composed primarily of nitrogen and oxygen, with carbon dioxide present in trace amounts measured in fractions of a percent. Water vapor fluctuates with weather and climate, cycling continuously between ocean, land, and sky. On Venus, by contrast, carbon dioxide dominates at roughly 96% of the atmosphere, with nitrogen forming most of the remainder. Oxygen is nearly absent, and water exists only in minute traces. The chemistry of each sky reflects the pathways their planets followed over billions of years, one shaped by active cycling and liquid reservoirs, the other by accumulation and loss. Surface pressure reveals an equally stark difference. At Earth's sea level, the atmosphere exerts a pressure defined as 1 bar. On Venus, the weight of the overlying carbon dioxide column produces pressures exceeding 90 bars. This disparity alters not only comfort or survivability, but the physical behavior of gases, the boiling point of liquids, and the mechanical stresses on any structure exposed to the environment. Earth's atmosphere allows liquid water to remain stable across broad regions. Venus's surface conditions prevent such stability entirely. Rotation introduces another contrast. Earth completes one spin in approximately 24 hours, distributing sunlight in a daily rhythm that shapes weather systems and biological cycles. Venus rotates once every 243 Earth days and does so in a retrograde direction. This slow, reversed motion contributes to atmospheric dynamics distinct from those of Earth, influencing circulation patterns and the interaction between solar heating and planetary rotation. Despite this difference, Earth's rapid spin works in concert with its oceans and atmosphere to moderate temperature contrasts, while Venus relies on dense air and high-altitude winds to achieve uniform heat distribution. Magnetic fields further separate the two worlds. Earth's internally generated magnetosphere deflects much of the solar wind, reducing the rate at which atmospheric particles escape into space. Venus lacks a comparable global magnetic shield, allowing direct interaction between its upper atmosphere and solar particles. Over geological time, this difference influences the retention of lighter elements and shapes atmospheric evolution in subtle but cumulative ways. When considered together, these contrasts illustrate how small initial variations can amplify across epochs. A slightly closer orbit alters energy balance. Differences in rotation affect internal dynamics and atmospheric tides. Variations in heat flow determine whether a dynamo persists. The presence or absence of sustained liquid water governs carbon cycling and chemical feedbacks. None of these factors operates in isolation. Each interacts with the others, reinforcing trends and guiding the planet toward a particular equilibrium. Earth and Venus began with comparable materials and similar scales, yet the interplay of orbital distance, internal structure, atmospheric chemistry, and long-term feedbacks carried them along diverging paths. Their present states are not accidents of size, but outcomes of cumulative processes, demonstrating how planetary systems respond to subtle differences with results that, over billions of years, become unmistakably distinct. Around every star, there exists a range of distances where liquid water can remain stable on a planetary surface, provided an atmosphere of suitable composition is present. This region is known as the habitable zone, not because it guarantees life, but because it allows temperatures compatible with liquid water under the right conditions. The position of this zone depends on stellar luminosity, atmospheric physics, and planetary albedo. Too close to the star, water evaporates irreversibly. Too far, it freezes into permanent ice. Venus orbits near what is considered the inner edge of the Sun's habitable zone. Early in the solar system's history, when the Sun shone with less intensity than it does today, that inner boundary lay closer to the star. Climate models suggest that Venus may once have resided within or just inside this shifting margin, where modest greenhouse warming could have sustained surface water for a time. Its proximity to the threshold meant that only slight changes in atmospheric composition or solar output would influence whether oceans endured or vanished. Stars do not remain constant in brightness. As the sun fuses hydrogen into helium in its core, the balance of pressure and temperature shifts gradually. Over billions of years, solar luminosity increases as the core contracts and heats, driving more vigorous fusion reactions. Since its formation, the sun's output has risen by roughly 30%. This slow brightening alters the extent of the habitable zone, pushing its inner edge outward over time. For a planet positioned close to that boundary, gradual stellar evolution can have cumulative consequences. An increase in solar energy input raises surface temperatures incrementally. Higher temperatures enhance evaporation, thickening the atmosphere with water vapor, which strengthens the greenhouse effect. As previously described, this feedback can move a planet toward conditions where outgoing infrared radiation cannot compensate for incoming solar energy. Once that threshold is crossed, surface water becomes unstable. Venus, receiving nearly twice the solar flux that Earth receives today, would have experienced these changes more acutely. Even during epochs when the sun was dimmer, its orbital position ensured elevated baseline temperatures relative to Earth. As solar brightness increased, the delicate equilibrium that may once have permitted shallow seas would have become more difficult to maintain. The habitable zone itself migrated outward, leaving Venus progressively closer to the regime where liquid water could not persist. Long-term solar evolution continues. Billions of years from now, as hydrogen in the core becomes increasingly depleted, the sun will expand and brighten further, eventually transforming into a red giant. The habitable zone will shift outward accordingly, rendering Earth's surface inhospitable long before that final stage. The concept of habitability, therefore, is not fixed but dynamic, tied to stellar life cycles as much as to planetary properties. In this broader context, Venus represents a world that likely crossed the inner boundary of habitability early in solar history. Its proximity to the Sun placed it near a tipping point that moved gradually but inexorably. As stellar luminosity rose, the margin narrowed, and atmospheric feedbacks amplified the change. The habitable zone, once encompassing Venus under certain conditions, retreated outward, leaving the planet in a domain where liquid water could no longer endure. The interplay between orbital distance and stellar evolution thus shapes planetary destinies across deep time, defining not only where life might arise, but how long favorable conditions can persist. Climate does not always change in smooth, proportional steps. In many systems, gradual forcing accumulates quietly until a boundary is reached, after which the response accelerates and settles into a new state. Such boundaries are known as tipping points. They are not moments of sudden external impact, but thresholds inherent to the structure of the system itself. Once crossed, returning to prior conditions becomes difficult or impossible because internal feedbacks begin to reinforce the new direction of change. A tipping point emerges when positive feedback loops dominate over stabilizing influences. In climate systems, feedbacks arise from interactions between temperature, atmospheric composition, clouds, ice, and surface properties. A modest increase in temperature may enhance evaporation, increasing water vapor and strengthening the greenhouse effect. Melting ice reduces reflectivity, allowing more sunlight to be absorbed and raising temperatures further. These processes are self-reinforcing. As they intensify, the system can move toward a qualitatively different equilibrium. Planetary climate models attempt to capture these dynamics through equations that represent radiation, balance, atmospheric chemistry, and fluid motion. By adjusting variables such as stellar flux, greenhouse gas concentration, and albedo, scientists can simulate how a planet's surface temperature responds over time. In these models, tipping points appear as critical values where the relationship between input and response changes abruptly. For example, as solar input increases incrementally, surface temperature may rise gradually until a threshold is reached, beyond which oceans evaporate rapidly and infrared cooling becomes insufficient. The system then shifts to a hotter, stable state. Venus offers a natural laboratory for understanding such thresholds. Its present condition reflects the outcome of feedbacks that likely intensified beyond recovery. A combination of proximity to the sun, increasing solar luminosity, volcanic outgassing, and water vapor amplification would have nudged the climate toward a boundary. Once liquid water became unstable, the feedback between evaporation and greenhouse warming would have accelerated the transition. The disappearance of oceans removed a major stabilizing mechanism, preventing reversal. Importantly, tipping points are not limited to extreme planetary transformations. Even within moderate climates, certain components can exhibit threshold behavior. Ice sheets, ocean circulation patterns, and atmospheric chemistry can respond non-linearly to gradual forcing. Modeling these processes requires careful attention to initial conditions and interactions among subsystems. Small differences at the outset can lead to divergent trajectories over long timescales. The lesson drawn from Venus is rooted in physics rather than in rhetoric. Climate systems operate under definable laws governing radiation, thermodynamics, and fluid dynamics. Feedback loops can either dampen change or amplify it, depending on context. When amplifying processes exceed stabilizing ones, a tipping point may be approached. The outcome is not arbitrary, but determined by the balance of energy flows and chemical exchanges. By studying Venus, scientists refine their understanding of how planetary climates respond to sustained forcing. The planet stands as evidence that equilibrium states are contingent upon thresholds that, once crossed, lead to durable transformations. In this way, Venus deepens insight into the behavior of complex climate systems, illustrating how gradual influences can accumulate until a new and persistent condition takes hold. Guided by the internal logic of feedback and balance, a small difference in distance can shape an entire planetary destiny. Earth orbits at approximately 1 AU from the Sun, receiving less solar energy than Venus at 0.72 AU. That fractional separation reduces the total incoming radiation significantly, placing Earth farther from the inner boundary where liquid water becomes unstable. In the early solar system, when the sun shone more faintly, this difference may have been subtle. Over billions of years, as solar luminosity increased, that modest outward position provided additional margin, allowing surface temperatures to remain within a range compatible with persistent oceans. Yet distance alone does not account for Earth's enduring stability. Beneath its surface, Tectonic plates move slowly across the mantle, fragmenting and recycling the crust. This mobility allows carbon dioxide to cycle continuously between atmosphere, ocean, crust, and interior. When volcanic outgassing raises atmospheric carbon dioxide, increased temperatures enhance weathering reactions that draw carbon into carbonate rocks. Through subduction, some of that carbon returns to the mantle, later re-emerging in measured quantities through volcanism. The system operates over immense spans of time, adjusting gradually to perturbations and preventing long-term accumulation. Stable oceans are central to this regulation. Liquid water dissolves carbon dioxide, moderates temperature through its high heat capacity, and enables chemical reactions that lock carbon into solid minerals. Oceans also redistribute energy through currents, smoothing regional contrasts and maintaining climatic balance. Their persistence ensures that evaporation and condensation remain part of a closed cycle rather than a one-way transition to atmospheric dominance. As long as water remains liquid across large areas, it acts as both a buffer and a participant in atmospheric chemistry. Earth's magnetic field adds another layer of protection. Generated by convection within its molten outer core, the magnetosphere deflects much of the solar wind, reducing the rate at which light atmospheric constituents escape into space. Hydrogen loss still occurs, but at a pace far slower than would be expected without magnetic shielding. By preserving volatiles, including those derived from water, the magnetic field contributes indirectly to the maintenance of oceans and atmospheric stability over geological timescales. The interplay among these factors creates a network of stabilizing feedbacks. Greater orbital distance limits baseline heating. Active tectonics regulates carbon dioxide. Oceans provide thermal inertia and chemical sinks. The magnetic field mitigates atmospheric erosion. None of these elements alone guarantees temperate conditions, yet together they form a resilient system capable of absorbing gradual changes without crossing irreversible thresholds. Earth's climate has shifted repeatedly throughout its history, from greenhouse periods to ice ages, yet liquid water has remained a constant presence. The planet's internal dynamics and orbital placement have allowed feedback mechanisms to operate effectively, preventing the amplification that transformed Venus. The divergence between the two worlds emerges not from a single cause, but from the cumulative effect of distance, geology, chemistry, and magnetism interacting over billions of years. In this convergence of factors, Earth avoided the path toward permanent runaway heating. Its position relative to the Sun, combined with dynamic interior processes and sustained oceans, maintained a balance that Venus could not preserve. The outcome illustrates how intertwined systems can sustain habitability when multiple stabilizing mechanisms operate together, each reinforcing the others across deep time. Far in the distance of deep time, long after present climates and continents have shifted beyond recognition, the sun itself will continue a gradual brightening that began in its earliest youth. Stellar physics shows that as hydrogen fuses into helium within the core, the sun's luminosity increases incrementally. Over hundreds of millions of years, the change is subtle, yet across billions, it becomes decisive. Each increment adds slightly more energy to Earth's surface, narrowing the margin that has long allowed liquid water to persist. Climate models that extend forward across immense spans suggest that as solar output rises, average temperatures will climb in response. Increased warmth would enhance evaporation from oceans, raising atmospheric water vapor. Because water vapor is an efficient greenhouse gas, additional vapor would amplify the warming, reinforcing the trend. Over sufficiently long intervals, this feedback could approach a threshold at which oceans begin to shrink permanently, not from sudden boiling, but from a sustained imbalance between incoming energy and outgoing radiation. The process would unfold gradually on geological timescales, measured not in centuries, but in hundreds of millions to billions of years. Simulations indicate that within roughly 1 to 2 billion years, rising solar luminosity may drive Earth toward a moist greenhouse state. In such a regime, water vapor becomes abundant in the upper atmosphere, where ultraviolet radiation can break apart molecules, allowing hydrogen to escape to space. Loss of hydrogen represents a net loss of water, since oxygen alone cannot reconstruct the original molecule without a source of hydrogen. Over extended periods, this escape would thin the oceans, altering atmospheric chemistry and climate in ways that could eventually resemble aspects of Venus's history. Yet these projected transformations lie far beyond human timescales. Current understanding of Earth's climate system shows no imminent trajectory toward a Venus-like runaway greenhouse under natural solar evolution. The sun's luminosity increases by roughly 10% every billion years, a pace that allows planetary feedback mechanisms to operate over long intervals. While anthropogenic influences can modify climate significantly within centuries, the catastrophic evaporation of global oceans requires sustained radiative forcing far greater than present conditions. In the near term of human civilization, such an irreversible transition remains unlikely. Earth's long-term future will involve stages of gradual warming, shifts in ecosystems, and eventual changes to ocean stability as solar output continues to rise. Before any complete ocean loss occurs, complex life would face profound environmental stress. Farther ahead, perhaps several billion years from now, the sun will enter a red giant phase, expanding and altering the inner solar system dramatically. By that era, surface conditions on Earth would already have diverged substantially from those familiar today. The comparison with Venus highlights the role of timing and thresholds. Venus likely crossed its critical boundary early, when higher solar input and internal dynamics combined to drive runaway heating. Earth occupies a position where similar physics may unfold only after immense stretches of time. The divergence is therefore not permanent immunity, but deferred consequence, governed by stellar evolution and planetary feedbacks interacting across eons. In this perspective, Earth's habitability appears as a phase within a larger stellar life cycle. The same processes that sustain warmth and energy also carry the seeds of eventual transformation. For now, oceans endure, tectonics continue, and the carbon cycle moderates atmospheric composition. The future path toward a hotter state remains distant, embedded in the slow brightening of the sun and the patient arithmetic of planetary climate over billions of years. Beyond our solar system, thousands of distant stars now reveal small shadows crossing their light, subtle dimmings that betray the presence of rocky worlds. Space telescopes have cataloged planets comparable in size to Earth, orbiting within ranges once thought rare. Many of these bodies circle close to their stars, completing orbits in days or weeks, bathed in intense radiation. At first glance, a planet similar in radius to Earth might suggest familiar terrain, yet size alone conceals profound differences in climate and atmosphere. As detections accumulated, astronomers began to recognize that some of these rocky exoplanets likely resemble Venus more than Earth, a planet only slightly nearer to its star than the traditional habitable zone can experience sustained heating strong enough to evaporate surface water. Without liquid oceans to absorb carbon dioxide and regulate temperature, atmospheric greenhouse gases may accumulate unchecked. The result can be a dense, carbon dioxide rich envelope, thick clouds, and surface conditions hostile to stable liquid water. Such planets occupy what researchers informally describe as a Venus zone, a region interior to the habitable zone where runaway greenhouse states become probable. Distinguishing between Earth like and Venus like worlds has become a central challenge in planetary science. Transit observations reveal a planet's size and orbital period, while radial velocity measurements estimate mass. Together, these data provide density, offering clues about composition. Yet density cannot reveal atmospheric chemistry directly. To probe atmospheres, astronomers analyze starlight filtered through planetary skies during transits or emitted as thermal radiation. Spectroscopy can identify molecules such as water vapor, carbon dioxide, methane, or oxygen, each imprinting characteristic absorption features. Interpreting these signals requires careful modeling, since clouds, photochemistry, and stellar radiation all shape the resulting spectrum. The distinction carries profound implications for the search for life. A planet located within a star's nominal habitable zone may still have lost its oceans long ago, while another slightly farther out may retain temperate conditions. Stellar type further complicates the picture. Around red dwarf stars, habitable zones lie closer in, exposing planets to intense stellar flares and high energy radiation that can erode atmospheres. Around brighter stars, habitable zones shift outward, but long term stellar evolution alters boundaries over time. Understanding where a Venus like transformation becomes likely helps refine which worlds merit closer scrutiny for biosignatures. The growing catalog of rocky exoplanets has therefore expanded the narrative beyond a simple Earth analog search. It has revealed that planetary outcomes span a spectrum from frozen deserts to water worlds to dense greenhouse spheres. Venus provides a tangible example of how a planet close to a star can diverge dramatically from Earth despite similar size and composition. By studying its history, scientists refine climate models that can be applied to distant systems, estimating which exoplanets may harbor stable oceans and which may be shrouded in opaque, superheated atmospheres. As new observatories analyze exoplanet atmospheres with increasing precision, the challenge remains to disentangle signals shaped by clouds, chemistry, and stellar influence. Each detection contributes to a broader statistical understanding of how common temperate, ocean bearing planets might be. The recognition of a Venus zone underscores that habitability is not defined by size alone, but by the delicate interplay of radiation, atmospheric dynamics, and planetary feedbacks. In that expanding census of distant worlds, Earth and Venus stand as contrasting templates, guiding interpretation across the galaxy. After decades in which attention drifted outward toward Mars and the icy moons, a renewed focus has begun to settle on the bright morning star. Venus, long regarded as a hostile endpoint of planetary evolution, is once again becoming a destination. Advances in instrumentation, modeling, and data analysis have reshaped the scientific questions, revealing that many of the most important uncertainties about its past and present remain unresolved. With that recognition, new missions have been selected to return, not merely to glimpse the planet briefly, but to study it with sustained precision. One of these missions is NASA's DAVINSI, an acronym for Deep Atmosphere, Venus Investigation of Noble Gases, Chemistry, and Imaging. Rather than orbiting alone, DAVINSI will release a descent probe designed to plunge through the thick atmosphere, sampling gases directly as it falls. By measuring noble gas abundances and isotopic ratios, The mission aims to reconstruct aspects of Venus's early history, including clues about the presence and duration of ancient water. As the probe descends, cameras are expected to capture high-resolution images of tessera terrain, complex highland regions whose structure may preserve records of the planet's earliest crust. The descent itself becomes an experiment in chemistry and physics, tracing temperature, pressure, and composition layer by layer. Complementing this approach is NASA's Veritas mission, short for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. Veritas is designed to orbit the planet and map its surface using advanced radar systems capable of far higher resolution than previous surveys. By measuring surface deformation and emissivity, it will search for signs of active volcanism and refine understanding of crustal composition. Detailed topographic maps may reveal whether tectonic style differs fundamentally from Earth's plate-driven processes, or whether more subtle forms of deformation operate beneath the stagnant lid. Across the Atlantic, the European Space Agency is preparing the Envision mission. Envision will also orbit Venus, employing radar and spectrometers to probe both surface and atmosphere. Its instruments are intended to investigate interactions between volcanic activity and atmospheric chemistry, linking interior processes with climate evolution. By comparing mineral signatures with gas abundances, scientists hope to determine whether present-day eruptions continue to inject sulfur dioxide and other compounds into the clouds. The resurgence of Venus exploration reflects a broader shift in planetary science. Understanding why Venus diverged so dramatically from Earth informs models of climate stability, atmospheric loss, and planetary habitability. Data from earlier missions, including the Soviet Venera landers and the Magellan orbiter, provided foundational insights, yet many questions remain open. Improved technology now allows measurements once considered impossible, including precise isotopic analyses and detailed radar interferometry capable of detecting subtle surface changes. There is also a strategic dimension. As exoplanet discoveries multiply, interpreting distant rocky worlds depends on understanding the full range of outcomes within our own solar system. Venus serves as a nearby laboratory for runaway greenhouse processes, cloud chemistry, and surface resurfacing events. By studying it directly, scientists refine the templates applied to planets orbiting other stars. In this renewed effort, Venus is no longer seen solely as a cautionary example, but as a complex system awaiting deeper exploration. The forthcoming missions represent a coordinated attempt to integrate atmospheric chemistry, surface geology, and interior dynamics into a coherent narrative. Through descent probes and orbital mapping, the planet's story may become clearer, revealing how a world so similar in size to Earth followed such a different path. In the pale light of dawn or dusk, Venus shines with a steady brilliance, serene to the unaided eye. From a distance it appears calm, almost gentle, yet beneath that brightness lies an archive of extremes written in rock, gas, and heat. Without uttering a word, the planet preserves a record of physical processes carried to their limits. It stands not as a symbol, but as a system, a world whose present state reflects the cumulative consequences of radiation, chemistry, and interior dynamics unfolding across billions of years. Scientists often describe Venus as a natural laboratory because it allows fundamental principles of climate physics to be observed in their most amplified form. The greenhouse effect, subtle and life-enabling on Earth, reaches saturation there. Carbon dioxide dominates the atmosphere, trapping infrared radiation until surface temperatures remain nearly uniform from equator to pole. Clouds composed of sulfuric acid reflect much of the incoming sunlight, yet the energy that penetrates cannot easily escape. The balance between absorption and emission has shifted irreversibly, revealing how radiative transfer operates when feedbacks reinforce rather than stabilize. By examining isotopic ratios, atmospheric circulation, and volcanic resurfacing, researchers trace the arc of planetary evolution. They reconstruct how early conditions may have differed, how water was lost, how crust and mantle interacted without plate tectonics to recycle carbon gradually. Venus demonstrates that planetary climates are not fixed states, but trajectories shaped by initial parameters and long term feedbacks. Slight variations in distance from a star, rotation rate, or interior heat flow can alter atmospheric chemistry enough to redirect a planet's path. This perspective extends beyond a single world. When scientists compare Earth and Venus, they are not seeking moral lessons but boundary conditions. Venus shows what occurs when stabilizing cycles fail to counter rising greenhouse gases and when oceans, once present, cannot persist. Its dense atmosphere and crushing pressure illustrate the physical consequences of unchecked accumulation. The absence of a global magnetic field highlights the role of planetary interiors in shielding atmospheres from solar wind erosion. Each factor becomes a data point in a broader framework for understanding rocky planets. The phrase Earth's cautionary twin arises from this comparative approach. Both planets formed from similar materials in the inner solar system and share comparable size and mass. Yet their divergence underscores sensitivity within coupled systems. Climate, geology, and stellar radiation do not operate independently. They interact in loops that can either dampen disturbances or amplify them. Venus embodies the amplified case, a reference model for runaway processes and threshold behavior. Studying Venus refines climate models used not only for Earth, but for exoplanets orbiting distant stars. It tests equations governing convection, cloud microphysics, and radiative balance under extreme conditions. It informs estimates of habitable zone boundaries and the likelihood that a rocky planet retains liquid water over time. In this sense, Venus contributes silently to the search for life elsewhere, helping to distinguish between worlds that may sustain oceans and those that have crossed irreversible boundaries. The planet offers no commentary, yet its atmosphere, surface, and interior provide measurable evidence of how planetary systems evolve. By decoding that evidence, scientists gain a clearer view of the delicate interplay that sustains temperate conditions on Earth. Venus does not speak, but through spectroscopy, radar mapping, and descent probes, its history becomes legible, expanding understanding of climate physics and planetary destiny across the cosmos. At ground level, the air would feel less like wind and more like weight. Movement exists, yet it carries none of the familiar whisper or rush associated with Earth's breezes. The atmosphere is so dense that sound travels differently, its speed altered, its texture muted and compressed. Any vibration would be shaped by carbon dioxide, thick enough to behave almost like a fluid under pressure. Instead of sharp gusts or rustling leaves, there would be a heavy stillness, a subdued transmission of energy through gas that presses with the force of an ocean. The sky above would not appear blue or black, but a uniform amber, filtered through layers of cloud composed of sulfuric acid droplets. Sunlight struggles downward, scattered and diffused until shadows soften and horizons blur. The illumination resembles a perpetual late afternoon, yet it never transitions into night in the way Earth does. Because the atmosphere redistributes heat so efficiently, temperature differences between day and night remain minimal. Darkness falls gradually, but the thermal environment changes little, maintaining an almost constant intensity across latitudes and longitudes. On the surface, rocks rest beneath this unchanging glow, shaped not by rivers or rain, but by volcanic outpourings and tectonic stresses. There are no streams carving channels, no waves smoothing shorelines, no cycles of freezing and thawing to fracture stone. Without liquid water, erosion proceeds slowly through chemical reactions with the atmosphere and the gradual settling of dust. The landscape retains the imprint of lava plains and shield volcanoes mapped by radar, their contours preserved because there is little to wear them away. The density of the air also alters the character of sound itself. If a probe or instrument emitted a tone, it would propagate efficiently through the thick medium, yet high frequencies would dampen rapidly. The result would be a low, muffled acoustic environment, devoid of the layered complexity found in terrestrial forests or oceans. Earlier landers that survived briefly on the surface transmitted data through this pressure, enduring temperatures capable of melting lead. Their mechanical systems operated within an environment that feels more static than stormy, dominated by heat rather than turbulence. The absence of water defines not only the terrain, but the atmosphere's chemistry. With no oceans to cycle carbon or to buffer temperature swings, carbon dioxide remains dominant. Clouds reflect much of the sun's light, contributing to the planet's brightness as seen from space. Yet the surface remains sealed beneath a persistent greenhouse blanket. The ground temperature, hot enough to soften many metals, changes little from equator to pole, reinforcing the impression of a world locked in thermal equilibrium at an extreme. This constancy creates a paradoxical stillness. There are winds aloft, racing around the planet in superrotation, yet at the surface their influence is subdued by density and friction. Dust may move slowly, but not in swirling tempests like those on Mars. Instead, the environment conveys an impression of suspension, as though time advances while the landscape remains fixed in its configuration. In that dense air and amber light, Venus presents a surface that is neither violently dynamic nor gently eroding. It is a realm where heat persists without relief, where sound is altered by pressure, and where the absence of water leaves geology exposed, yet scarcely transformed. The silence is not the absence of physics, but the culmination of it, a steady state shaped by atmosphere, composition, and the enduring consequences of a runaway greenhouse long ago. In the early architecture of the solar system, two neighboring spheres condensed from similar materials orbiting the same star, shaped by comparable forces of accretion and heat. Their masses settled into near equality, their compositions aligned in rock and metal, their beginnings almost indistinguishable against the glow of a young sun. Time, however, does not preserve symmetry. Across millions and then billions of years, incremental differences accumulated, subtle at first, then decisive. Venus drifted along a path where solar energy, atmospheric chemistry, and internal dynamics reinforced one another toward heat retention. Oceans that may once have pooled upon its surface could not endure the feedbacks that intensified warming. Water vapor rose, hydrogen escaped, carbon dioxide persisted. Geological processes operated without the moderating exchange of plate tectonics. The result was not an abrupt catastrophe, but a gradual transformation, a climate carried past a threshold from which it could not easily return. Earth followed a narrower corridor, slightly farther from the sun, endowed with active tectonics and long-lived oceans. It sustained cycles capable of absorbing disturbances. Carbon moved between atmosphere and crust. Heat circulated through currents and winds. Magnetic shielding reduced atmospheric loss. None of these elements acted alone. Together, they formed a network of interactions that maintained liquid water and moderated extremes. The divergence between the two planets emerged from this interplay, not from a single dramatic event, but from compounded feedbacks unfolding over deep time. The comparison reveals how planetary systems depend on balances that are both resilient and fragile. Radiative transfer, atmospheric composition, interior heat flow, orbital distance, and stellar evolution operate simultaneously, each influencing the others. Small variations in any one parameter can shift the equilibrium point. Once certain limits are crossed, feedbacks amplify change rather than counter it. Stability, therefore, is not a static condition but an ongoing negotiation among physical processes. Looking outward to other stars, this realization informs the interpretation of distant rocky worlds. Some may resemble Earth in size, yet trace trajectories closer to Venus. Others may occupy temperate zones temporarily before stellar brightening alters their climates. The story of these two neighboring planets becomes a template for understanding how common, enduring habitability might be across the galaxy. Within our own solar system, the contrast remains quietly present. One planet is cloaked in dense clouds, its surface locked beneath extreme heat and pressure. The other carries oceans, shifting continents, and a climate that, while dynamic, remains within bounds that allow life to flourish. Both outcomes arose from nearly identical starting conditions. The difference lies in how feedbacks interacted with distance, rotation, interior structure, and atmospheric evolution over immense spans. This perspective does not frame Venus as an anomaly, nor Earth as invulnerable. Instead, it highlights the delicacy inherent in planetary systems. The factors that sustain equilibrium can also drift, responding to stellar evolution and internal change. Over billions of years, even Earth's stability will adjust as the sun grows brighter. The present era of temperate oceans is a phase within a longer cosmic narrative. Two worlds share one solar system, orbiting the same star, reflecting the same light. Their divergence underscores how finely balanced conditions must be for liquid water to persist. In that understanding lies a quiet recognition. Planetary stability emerges from complex interactions, and its continuation depends on the sustained alignment of forces that, though governed by physics, never remain entirely fixed.